Lesson 31, Characteristics of Waves. In this lesson, we are going to build on what you already learned in Lesson 26. We'll also be using some of the terminology that you would also seen when you watched the Bill Nye episode before Lesson 26. We only have one objective for this lesson, and that is to be able to describe a wave by its characteristics. So let's take a look at some of these characteristics. And actually, the first thing is not really part of the wave itself. It's part of the medium. It's what we refer to as equilibrium. Now, you've seen the term equilibrium before when we talked about forces. In that case, it's when all the forces canceled and the net force was zero. In this case, it's what the medium would look like if no wave were traveling through it. Since the waves that we're going to be taking a look at are going to be transverse waves, we are going to represent equilibrium as a straight line. That is, a line with no wave. Next, we have what are called in-phase points. In-phase points are any two points along a wave that are the same distance from equilibrium and are vibrating in the same direction. Besides in-phase points, we also have out-of-phase points, which are any two points that are not in phase. Let's take a look at what this is like. Here we have our transverse wave with our equilibrium line. Each of these red dots represents a point that would be in phase. They are all the same distance from equilibrium, and they're vibrating in the same direction, in this case, upward. Each of these blue dots also represents points which are in phase. They're all the same distance from equilibrium, but vibrating downward. Now, the red dots and blue dots are not in phase. Even though they are the same distance from equilibrium, they are not vibrating in the same direction. The red are going up and the blue are going down. Both of those criteria must be met for points to be considered in phase. Next, we have what we call the amplitude of the wave. The amplitude is the maximum movement from equilibrium. Or, in the case of a transverse wave, we can say it's the height of a wave. We will be symbolizing it as a capital letter A. And although a capital letter A is also used for area, there's going to be no formula that is going to involve amplitude, so it shouldn't be confusing. Since amplitude is a distance, it's going to be measured in units of distance, such as millimeters or centimeters or even meters. The easiest way for us to determine this is to measure the distance from equilibrium to either a crest or a trough. Either one will give you the same distance. One of the things about amplitude is that it does indicate how much energy a wave has. The higher the wave, the more energy it has. So think about an ocean wave. A regular ocean wave has a certain amount of energy. But if we have a much larger ocean wave, like a tsunami, it required a lot more energy to create it, and it has a lot more energy. So the height of the wave indicated how much energy was actually in the wave. The next characteristic is the wavelength. The wavelength is the distance between any two consecutive in-phase points. Remember, consecutive means one right after the other. Probably the easiest way to measure the wavelength is to measure the distance between two consecutive crests or two consecutive troughs. The symbol that we're going to use to represent wavelength is a Greek letter. Since we've already used an L for length, we use a Greek letter L, called lambda. It kind of looks like an upside down Y. The lambda that's shown here is a printed lambda, in much the same way as the G in wavelength is a printed G. Nobody really makes G's like that. So the easiest way to make this is to make as though you're making an X, and just don't make the upper right hand corner. And that's your lambda. And since wavelength is also a length, it's also going to be using units of distance: centimeters, millimeters, meters. Next, we have what's called the period of the wave. And when we talk about period, we generally mean time. A class period is 42 minutes long, and it repeats itself over and over again. A time period of a decade is 10 years long, and it's always 10 years and repeats itself. So the period is the time it takes for one wave to pass. Since period is a time, the symbol that we're going to use to represent it is a capital letter T. We don't use a lowercase t because lowercase t stands for time in general. Since this is a special time, we're using a capital letter T. And the unit, since most waves travel very, very quickly, is going to be seconds. Our last characteristic is called the frequency of a wave. The frequency is the number of complete waves that pass each second. And we say each second because, once again, most waves travel fairly quickly. The symbol that we use to represent frequency is a lowercase f. The unit, since we're counting how many waves per second, is waves per second. And waves per second, much like any other units, gets another name. We call it a hertz, named after Heinrich Hertz, who studied radio waves. And hertz, like Pascal's, uses a two-letter abbreviation, in this case, Hz. Now, to give you an idea about how fast waves travel, if you think of a radio station, for example, if the radio station was 99.9, 99.9 actually represents the frequency of the wave. It's not 99.9 hertz though, it's 99.9 megahertz. Remember that the prefix mega means a million, so that would be 99.9 million hertz, or 99.9 million waves per second that are passing your antenna. So most waves do travel fairly quickly. Now here's a drawing with some of the things that we talked about: the equilibrium, amplitude, and wavelength of a wave. You'll want to draw this in your notes so that you have something to refer to. Now, something else. When you're doing your worksheet today, what's going to happen is they're going to ask you to find or to determine the amplitude, wavelength, period, and frequency of a series of waves. So let's see how you'll do that. First, in order to find the amplitude, remember amplitude uses the symbol of a capital A, what you're going to do is you're going to use a ruler and measure either from equilibrium to a crest or from equilibrium to a trough. Make sure you have units. To measure the wavelength, you can measure from either crest to crest, or you can measure from trough to trough. Remember, they must be consecutive. Sometimes this isn't always going to be practical though, because you may not have two crests or two troughs. So every wave is made up of one complete crest and one complete trough. So you can always measure the distance of one complete crest and one complete trough. Remember that the symbol for wavelength is a lambda. You'll want to put that down, as well as the unit. Next, you'll be looking for the period. The period uses a symbol of a capital letter T, and it's the time it takes one wave to pass, or one complete crest and one complete trough. If we look at the picture, we see that it says time in seconds going along the bottom. There's a 0 and a 1, representing 0 seconds and 1 second. We have one complete crest, one complete trough, another complete crest, and another complete trough by the time we hit 1 second. So one complete wave is passing, or one crest and trough are passing, in half of that amount of time. So the period would be a half of a second. The frequency, symbolized as a lowercase f, is how many waves pass in 1 second. In this case, we have two complete crests and two complete troughs passing by the time we hit 1 second, which gives us a frequency of 2 hertz. or 2 waves per second. Now, sometimes it's going to be easier to determine the frequency instead of the period first, or vice versa, the period and then the frequency. And a relationship between period and frequency is this. If we rewrite 2 as 2 over 1, we can see that period and frequency are reciprocals of each other. So if you know one, all you have to do is take the reciprocal and it will give you the other. So those are some characteristics of waves that you need to be familiar with. The equilibrium, in-phase and out-of-phase points, the amplitude, wavelength, period, and frequency.